Hi there, welcome back again to our video lecture in engineering dynamics. In this video, we'll be solving our first problem for the polar coordinate system. This problem is taken from the textbook of R.C. Hibbeler, and it's actually the fundamental problem 12-34. The problem says the platform is rotating about the vertical axis such that at any instant its angular position, so this word is that's position, is theta is equal to 4t raised to 3 halves in radians. So that's the units of our angular position, where t is in seconds. A ball rolls outward along the radial groove so that its position is r is equal to 0. So let's remove this. Its position is r is equal to 0.1 t cubed in meters, where t is in seconds. Determine the magnitudes of the velocity and acceleration of the ball when t is equal to 1.5 seconds. So this is our disk, and if we try to draw this one in terms of XYZ axis, then let's say this is our X, this is our Y, and this is our Z axis. So it is rotating along this Z axis. So let's draw this one looking top view. So we'll try to view this in terms of XY plane. So XY plane, this is how it looks like. This is our X, this is our Y, and the Z is orthogonal to this plane, to this paper. And we have this ball that's rolling along this radial groove. When you say radial, it's actually going to the center. So okay, we'll make labels. So let's say this is our theta, and then we have a rotation along this z axis. So let's have a review first of our equations for the polar coordinate systems. So in this table, I have presented the kinematic variables, the velocity and acceleration, and its corresponding equation with respect to the radial axis and then the angular axis. So for VR, what we need is it's just actually the first derivative. So that's r dot, the first derivative of position, radial position. Whereas in this angular velocity, then that's gonna be our radius times the first derivative of our angular distance. So let's write units for now. When we say r, then that's gonna be our radial distance. Okay, so take note, when sometimes we just write r, but actually what we meant by that is the radial axis. But we also use the same symbol when we say r. It refers to the position of your point mass with respect to the axis of motion, or the axis as a reference point. So r is the radial distance, and that's in meters. Okay, and then if we take the first derivative of r, then that's gonna be the velocity. Okay, we can just write velocity, or if you want, radial velocity, and that's gonna be meters per second. And r double dot, and that's gonna be acceleration, and the unit is in meters per second squared. Now we have new variables here, the theta. So the theta, it just means that's our angular let's say angular position. And if it's angular position, then it just means our units here is just in regions. Theta dot is angular velocity, and the unit would be radians per second. Now theta double dot, that's angular acceleration, and the unit would be radians per second squared. Now sometimes in some reference, they, instead of using theta dot, they use let's say, okay, sometimes they use this symbol omega. So the units, when it's like we are separating these linear components and these angular components. So if the variables are in terms of linear components, then the units would be the typical ones, meters per second, and then this one, meters per second squared. But if we are talking about variables regarding the angular axis, then our units would be radians, or radians per second, or radians per second squared. Okay, so the question is, for example, if we are asked to solve for the velocity, let's say radial velocity, then we just have r dot, right? And the unit for this is meters per second. Now here, how about this, the angular velocity? So for this one, notice that this is as what we said, it's radians per seconds, right? But what is r? So you notice it's multiplied to our linear radius. So this radius is, let's say, in meters. So our unit would be meters per second. Okay, so this region unit is actually something like mysterious, because it just come and go, but it's actually a ratio between two distances, or between two lengths. So if it's a ratio, let's say that's meters per meters, then that unit is just equal to 1. So that is why radians, it's a unit that just come and go. Okay, so if you notice that once we have this r value, let's say our position, then we just take the derivative, the first derivative and the second derivative. And if we are also given with this angular value, angular displacement, then we just take the first derivative and second derivative. And you see that the equations here, they're just actually combinations of those derivatives of these two axes. So if the problem has given us, for example, r and theta, then what we should do is just to find the first derivative and the second derivative, and then we are good to go. So back to our problem, we have this platform rotating, and we're actually given with this angular displacement and this linear I mean, sometimes when I say displacement, I just mean position. Anyway, displacement is just simply a change in position. It's a delta theta. Okay, so this one is our angular position, and this r is our radial position, or sometimes I refer to it as linear position. Okay, so now we can solve this. So take note, this theta is a function of time. So meaning we can write this as, if we want to, we can write this as theta as a function of time. And the same goes true with our r. Even though it's not written as as a function of time in this notation, but we know that it's actually a function. So at whatever time t, then we will get a different r or theta value. But the problem is stated that we have to determine the magnitude of velocity and acceleration of the ball when t is equal to 1.5 seconds. So meaning we have to evaluate this r and this theta at 1.5. Okay, so let's try to solve. Okay, so first, finding the derivatives of r. So our r is equal to 0.1 t cubed. Now let's take the r dot. So r dot is just 0.3 t squared. And if we evaluate this at t is equal to 1.5, meaning if we substitute this value of t, this 1.5, to this t variable here, then what we get is, okay, we can write it as, okay, let's just write it, let's say 0.3 times 1.5 squared, then that's gonna be, okay, 1.5 squared times 0.3, and that's 0.675. Okay, so we'll take the second derivative, and r double dot is just equal to 0.6 t. Then if we evaluate this at t is equal to 1.5, by the way, sometimes I use this notation instead of writing this notation, so it doesn't matter, they're just mathematical symbols, but we are referring to the same thing. So 0.6 times 1.5, that's gonna be 0.9. So that's in meters. What about this one? So I think we also have to find this r value evaluated at t. So 0.1 times 1.5 cubed, and that's gonna be 1.5 cubed times 0.1, so 0.3375. Okay, so now we have our r dot and r double dot. So now let's solve for, I think we have to underline this. Okay, so next step is to solve for our for the derivatives of our angular position. So theta is equal to 4 t raised to 3 halves. Then if we evaluate this, then that's gonna be let's say t is equal to 1.5. So that's gonna be let's say 1.5 raised to 3 halves, 1.5 raised to 3 halves times 4. So that is 6.75 radians. Okay, so we take the first derivative, that's theta dot is equal to 4 times 3 halves, that's actually 6, so 4 times 3, 12 divided by 2, so that's 6 t, 3 halves minus 1, I think that's 1 half. Now if we evaluate this at t is equal to 1.5, what we get, so 1.5 raised to 0.5 times 6, then that's 7.348. Okay, next is theta double dot, so 6 divided by 2, that is 3, then 1 half minus 1 raised to negative 1 half. So we evaluate this at t is equal to 1.5, then what we get, raised to negative, I don't know what's the negative here in this calculator, negative 1 half. So try this. Okay, times 3. So what we get is 2.449 radians. Okay, so now we have this theta and its derivative plus the linear position and its derivatives. Okay, so now we can solve for, let's try. Okay, so solving for our first equation. Okay, so let's solve for the velocity. Our equation is just simply R, for the VR. By the way, what we're asked to find is the magnitude of velocity. So meaning it's just the scalar value of velocity. So our equation is this one. So v is equal to square root of vr squared plus v theta squared. Okay, so v is equal to square root of vr squared plus v theta squared. Now what is vr? So vr is just simply our r dot. So vr is 0.675 and our v theta is r theta dot. So that's r theta dot is equal to, so r, what is r? So our r is 0.3375 times theta dot, and theta dot is 7.348. So okay, 0.3375 times 7.348. So we have 2.4, let's say 2.45. So that's 2.45, and that's now in meters per second, and this one is also in meters per second. So therefore we can now solve for our velocity, which is just equal to 0.675 squared plus 2.45 squared. Okay, so 2.45 squared plus 0.675 squared, and shift the square root, shift answer. we have 2.54 meters per second. Okay, then now we solve for the acceleration. So solving for acceleration. Okay, so our A is just simply square root of AR squared plus A theta squared. Now what is AR? So AR is we have this R double dot minus R theta dot squared. So R double dot minus R theta dot squared. Now what is R double dot? We have, okay, this is our R double dot, 0.9 meters. We have 0.9 wait, I think this one should be meters per second squared, because this is an I think this should be meters per second squared, and then this one is meters per second. So sorry about that, because this is the second derivative, then that should correspond to a unit of acceleration, and this one first derivative, then that should correspond to a unit of velocity, which is meters per second. Okay, so what else? A minus R. Now what is R? 0.3375 times theta dot. Our theta dot is 7.348 times 7.348 squared. Okay, so 7.348 squared times 0.3375. Then we have 0.9 minus answer. Then we have 17, that's negative 17.32. That's in meters per second squared. Okay, so now let's solve for angular acceleration. For the angular acceleration, we will have A theta is equal to, this is the equation that we'll use. So R times theta double dot times theta double dot plus 2 times R dot times theta dot. Okay, so what is R? That's 0.3375 times theta double dot. Our theta double dot is 2.449 times 2.449, a plus, let's just write it here at the below, plus 2 times R dot, which is 0.675 times theta dot. Our theta dot is 7.348, so 7.348. Now we solve this one. We have 0.3375 times 2.449 plus 2 times 0.67 0.675 sorry, times 7.348. Okay, and we get 10.7, so that's 10.746. So now we can solve for acceleration. Acceleration is just simply the this value AR, so 17.32, okay, squared plus this 10.746 squared. Okay, let's square this one, that one, plus 17.32 squared, square root, shift, so that's 20.4, so 20.4 meters per second squared. Okay, so let's try to draw this one. So meaning that if this is our slot, and then this is our ball, then this ball, what do we get? Our velocity is positive. Okay, they're both positive, except for this acceleration, the radial. So if this is our radial, meaning a negative, then probably then it's actually decelerating, so meaning it's slowing down along this radial groove. So if let's check this problem, such that at any instant its angular position is, so a ball rolls outward along the radial groove, so meaning the motion of the ball is actually going outward, except that since this is negative, then it just means that it is slowing down. So that's the meaning of that, this one. Okay, so let's review our solution. So this problem is actually it's a lengthy problem, except that if you notice, once we have this linear position and angular position, what we did is just to find the derivatives, the first derivative and the second derivative, and after that actually we are good to go, because we have already this set of equations. So we just substitute the values, and then there we go, we can find the acceleration. So that's it. That's for these polar coordinate systems. Okay, so just a brief review. First, we find the derivatives of our linear position, and then the second step, we find the derivatives for our angular position, and then after that we solve for the velocity. So the velocity has two components, the radial component and then the angular component. So we first find this v sub r, and then v theta, and then we substitute, and then we get this 2.54 meters per second. Then after that we solve for the acceleration. So the acceleration has two components, and we first find this a sub r and then a sub theta, and then we take the square root of that value. So this is just really an easy problem. So in the next video, I think we'll be doing another problem for these polar coordinate systems, and we'll try also problems that relates from, let's say, rectangular coordinate systems to polar coordinate systems. Okay, so see you in the next video.